Yeah, you have the power. Yeah.
Okay, yeah, it looks like I have the power.
Yeah, there you go.
Yes, so uh, there it is. Okay, I don't know how to get rid of, let me, if I have the opzioni puntatore, yes. So, okay, so I have this thing, the laser, and then I don't remember how I can get rid of this bar on the top. I'm using a Zoom in the last 4 years for teaching, but I still,
Yeah, I mean,
anyway.
we don't see, okay, we don't, I don't know about your side, but on our side, we don't see, well, on my computer, I don't have.
Okay, perfect, perfect. Okay, okay. So I start, okay? First of all, good afternoon. And after 1 hour, you just switch off the computer, okay? Don't listen to me anymore. I don't know how long I will go, okay? I'm just quite lost in these topics. So David asked me to discuss with you structural geology and earthquake-related processes. So this is something we have been working on, myself and the group, several groups in the last 20 years. So there is quite a bit of stories to tell. Mainly, I work at the University of Padova, and these results also come with a long-lasting collaboration with the National Institute of Geophysics and Volcanology in Rome, plus some work I did when I was in Manchester for some years. Most of the research is funded by the European Union, not only the TREAD project, but many of the results I will show you today. I basically focused a lot on what we did with our group. Now there is this new nice group of people that we met. I met in Aix-en-Provence, including Naire, that was there, but she was not in this picture. Katere and Katere, I don't know how to pronounce it, and Jarod. So this is our TREAD dream team. And guys, good luck, ad majora, okay? And I'm an old guy, so we use these words in Italian: impara l'arte e mettila da parte. Learn the art and put it apart. So what I will talk with you today is, you will find a lot in this book by Chris Schultz. Sometimes it can be quite tough, direct, and also quite self-confident, not self-confident. I mean, he thinks he has some sharp ideas, and sometimes we can discuss about this. However, this is probably the best book you can find about the mechanics of earthquakes and faulting, including frictional processes. It's very complete. And however, I expect from you, change the art, okay, guys? Otherwise, there's nothing new here. Okay, learn it, but then change it. What I will discuss are why we are doing this. So why we spend time in structural geology and earthquakes, and some kind of fault processes, fault-related processes. And I will put together field studies, experimental studies, and numerical modeling to make some conclusions about the earthquake-related processes and how they are related to structural geology. Of course, we are very familiar with the damage produced by the earthquake. This is the Turkey-Syrian earthquake, 7.9. That was in February 2023, and about 60,000 people died. And look at this picture, okay? And now this is an example still from the Mediterranean. This is 1980, exactly the same picture. I would say that was, there is a missing dot point here. It was on November 1980. And this was in Italy, in southern Italy, Irpinia earthquake, and about 3,000 people died, okay? So clearly, to protect ourselves, that's the main point. We needed to build in a better way. Okay, they're still collapsing exactly the buildings exactly as 50 years ago, 43. This is a very interesting diagram I found out that is about the annual death from natural disasters by decade. That means that if you have 115,000 people dying because of natural disasters in this decade, this means that about 1.5 million people died in these 10 years. So this is the number of deaths per year. on average in 10 years. And you can see look at the red box. The red box are earthquakes, while the blue ones are drought, or you can have these turquoise colors, they're floods. Now you can notice that with the big droughts of the 20s, or the big floods of the 30s, and again droughts and so on, you have this exponential sort of, or linear to exponential decay of the number of deaths per decade. However, look at the red box, they're still there, and they just scatter a bit. Some of them are related to very big earthquakes. I don't know, this is probably the Sumatra earthquake, you know, in 2004. Only that earthquake plus the Haiti earthquake that was a few years later that made 500,000 of people died. So this makes the 50,000 on average in 10 years. But observe this, okay? And on average, we have about 12,000 people dying for earthquakes per year in this century and more. Just in Italy, 1,300 per year. This is, of course, related to some very big shocks that happened in Italy. For instance, in 1908, we have the Messina earthquake, about 100,000 people died just for that one. However, look at this decrease. Of course, the global population is increasing. So you would expect, of course, also the number of deaths to increase. This is not the case, but it's the opposite, and in particular, with the exception of earthquakes. Of course, this is telling you that we don't know much about earthquakes, and we are not able to manage them at all, it looks like. Of course, this is not considering what's going on, what will happen soon about climate change and the impact that in these kind of diagrams that we'll have here. This is why there is the question. However, clearly we know little about earthquakes. And well, what are they first in terms of their physics? In a very simple way, they are somehow related to the slip on surface. So this is a field picture of a natural fault. These are granitoid rocks, coins for scale. And you can see this white dike is a structural feature that has been displaced dextrally, dextral sense of shear, along this fault. This is the fault trace. And what we'll talk mostly in this talk is about friction coefficient, which is at the end the simple ratio of shear stress divided by effective or whatever normal stress. So this is an undimensional term. And of course, this is a very crude approximation, as you will see in this later in this talk. At that point, the other ingredient of an earthquake, because they are related to slip on surface, is the geometry of faults, which are, of course, are not flat. They are surfaces. They're not planar at all. This is the scale of 2 meters, and you can appreciate this waviness, okay? Then they are related to rupture processes, which is something I will not much discuss here. However, you have the nucleation of the earthquake maybe at some 8 kilometer depth, and then it propagates the rupture front a kilometer per second, okay? And while this happens, especially from the rupture tip, there is the emission of seismic waves. Of course, rupture process and the emission of waves and other processes, they are all related to the release of elastic strain energy, which is stored in the wall rocks, which this is driving rupture propagation. And this happens, of course, the propagation of the rupture along the fault. We can discuss about on-fault processes. So those that happen very near or within this, the core. I mean, I don't want to go much in details. Probably already Michele talked with you about this. But the rupture propagates probably in quite thin layers of rocks. The thickness of the fault gouge, whatever you call it, usually is a few centimeters. But then there is a lot also of off-fault damage, so nearby the fault, tens of meters, maybe more, depending on the magnitude of the earthquake and other properties of the host rocks that we call damage zone. And while the propagation occurs and there is radiation of seismic energy by means of elastic waves, you have all these processes occurring within the core here in this thin layer, So we call on fault, but also just outside of fault processes. And by off fault and on fault processes, we mean grain comminution, so grain size reduction due to fragmentation. And then a lot is about frictional heaving, because you are shearing rocks at high pressure, because they are at depth. Here they are at 7-8 kilometer depth. And there are some important numbers to consider. One is the velocity of the rupture that we can think is on average about 3 kilometers per second. This is just an average value. And then the velocity of slip. Again, this is an average value. So it's the relative motion of the two blocks at the size of the fault. This happens at an average speed of 1 meter per second. So if you think what's going on here at the tip of the rupture while it's propagating a kilometer per second, well, the rock here will suffer, let's say, an abrupt increase in stress operating there until the rock yields. This happens in nanoseconds, microseconds, so 10 to the minus 6 seconds. It's very fast what's going on here, milliseconds. And then there is an evolution of the strength of the fault during coseismic slip, this blue curve. At the same time, the slip rate increases, probably go up, we don't know exactly, maybe 100 meters per second for microseconds, and then drops down during sliding of the two blocks, and the average value is 1 meter per second. So clearly you have an evolution of slip rate and evolution of stresses, and especially we call, you can find several terms, but basically it's the dynamic strength of the fault. It varies a lot. And if you make the product of the two, it's a power. You see, this, we call it frictional power density dissipation. And some depth in the crust of 1 kilometer and more can be of the order of megawatts per square meter. So there is a lot of power dissipated, and this goes in thermal processes. So that you have a temperature increase there in the slip zone, but also in mechanical processes. So grain size reduction. And this is the, what you want for chemical reactions, for instance. Small grain size, high temperature, this helps the kinetics of any kind of reactions, which are quite complicated. And depending on the rock type, for instance, if you have carbonates, limestones, the one you find in the Central Apennines, you would expect that because of frictional heating, there will be breakdown of calcite, the rock-forming mineral, and so release of CO2, for instance. The extreme scenario is melting. So now, if you go here at the tip and look what's going on, well, you have the rupture propagating 1 kilometer per second. The rock basically is exploding at the rupture tip at these speeds, and then the blocks start to slide, in this case, dextrally. So the upper block is going to the right, the lower block of rock to the left, and the fault is going inside the screen. And rupture then is followed probably by fragmentation, and at some point in the extreme scenario, melting. So we have frictional melts. And this is what you see in the field. Okay, this is a COINFO scale here. So this is the thickness of this melt layer now solidified, produces an earthquake scar that is about 30 million years old. Okay, so events lasting few seconds are frozen in the rock for millions of years. So you can study these rocks to understand what's going on, at least in the continental crust made of granitoid rocks, and what happens down there during an earthquake. You can see also the injection here of the melt. So this is a crack that opened during rupture propagation. So it tells you also a lot about the stress field, the local stress field, the rotation of the stress tensor, and so on. And so you can start to make some questions, okay? Also for seismic hazard studies, and in general for physically based earthquake forecasting models. So what is of some relevance for us to understand is which are the physical and chemical processes active during an earthquake? What are the physical laws that describe fault strength during earthquakes? Why must seismic rupture propagate? This is the Gutenberg-Richter law Aurora was talking about. A lot of cracks, a lot of fractures propagate for a few centimeters, meters. Maybe they make magnitude -4, -3, 0, then we start to detect them -1, magnitude 1, 2, and so on. But very, very few becomes very large. Why? Then what is the energy budget of an earthquake? That's a really crucial question. And I mean, in physics, usually, I'm not a physicist, so I can say really wrong things here, but usually we start from energetic budgets to describe a process. They make the shortcut somehow. Here, we know very little about all this elastic strain energy stored in the rock, where this energy, how this energy is distributed, how much goes in seismic waves, how much goes in these on-fault processes, heat, comminution, how much goes in off-fault damage, where is this energy going? And seismological studies alone, right now, they don't allow us to address this question. I mean, they give constraints, of course, very relevant one about the source, the seismogenic source. So here basically goes what we did in the last, let's say, 20 years. We start from the field because we look at faults, as probably Michele told you a couple of weeks ago. And then we move to the microstructural studies. We want to understand the processes occurring during seismic faulting. So there is also a lot of microstructural studies. This is, the scale here is 2 microns, okay? So something at the micro scale to individuate the processes that may occur in natural faults. Then there is the part we work the most, I would say, at least I would in any case, so experiments. So we built machines to reproduce seismic sleep conditions in the lab, and we can detect also other signals, not only measure mechanical data, so what is the evolution of friction with sleep, sleep rate, sleep displacement, whatever, and get constitutive laws, but also we can detect acoustic emissions, so what we call the lab earthquakes, okay? Experimental, which have their own spectrum, and so on. Then the idea was to put all this together, what we can measure in the field, so including the fault roughness, and to model it, okay? And then by putting together what we get from the lab, from some constitutive laws of some kind that we discussed today, and then produce physically based earthquake models. This is something, of course, that people in this thread project will do very, using the most powerful codes available right now between the groups in Utrecht with the other one in Munich, for just to say some, but then there are other here. Nothing new in all this. Okay, we are just following the hint of this guy Severinus that at that time, we're talking about 400 and more years ago. Go, my sons, buy those shoes, clean the mountains, look at for the various kinds of minerals, not their character, and mark their origin. Okay, so go in the field, be inspired by the field, and then experiment. Okay, build furnaces, observe and experiment without cheating, and you will arrive. This is very, was very optimistic. You will arrive at knowledge of nature and the probability of things. So, well, I must say that Severinus was living in Denmark at that time. If you were in Italy, we used to burn people like him. I mean, Giordano Bruno was an interesting guy that we burned in 1600 in Rome because he was saying something similar, okay? No money, no science. You need money sometimes to do these things. So most of these results come from European grants. So there were about 4 million euros. And also researchers, different background, age, countries, and especially gender. That's crucial. So this is when we started many years ago, in 2009. There is the head of a physicist, Gianni Romeo. But then we have other people. This is me, very young now, like Stephen Smith, Andre Niemeyer. Some of them are advisors, supervisors now of some of the people listening. Marie Violet, she's a professor in EPFL now. She was a postdoc at that time. Elena is running the machine right now, and then other people here. Tom Mitchell is a full professor at UCL now. So they have different background. The number of girls increased in the years. That's quite good. So we have Chiara, Marike. So they did this group of people in about 10 years. They're working a lot about experiments and modeling. Shane Murphy was working with us for a while. Chiara and Stefano met in the lab, and now they got married. So something more than just a postdoc. Okay, I just go on because then there was also work in the field. We did quite a bit of work in the Central Apennines, and probably you listened to a bit of the results of Michele. Then he, of course, is running by his own. But then we have other people from INGV and also other former PhD students. You did a lot of work in the Southern Alps and also in the Atacama Desert. Michele is everywhere, basically. Now, these are the people starting recently. Here is Norway, they just started with you, but there are two postdocs, Wei and Simone here. The results I will show today, they are from them, most of them. Miriana and Silvia, they're doing the PhD here, including Wei Xin. And then Rodrigo is a postdoc working mainly now in the lab. I will show you some results perhaps at the end. So now it's passed about 20 minutes. Okay, so I have another 40 minutes, I think. So I hope I can make it. Structural geology and earthquake processes. Of course, you can interrupt me, please, if I go too fast or whatever, okay? Just stop me. I will move now from field studies, experimental studies, and numerical modeling. So we'll focus mostly on this side, field studies. So what we are very interested in, about this is the structural geology contribution, I would say, is the geometry. Geometry makes a lot. Probably this is something you will find out during your PhDs, how important is the network of faults, but also the roughness of individual surfaces in controlling the nucleation and the rest of the ruptures and other things. So at that time, we look at big outcrops. They are big. I mean, this is a glacier retreating, and you can recognize we are looking at places at the base of glaciers in that case, because glaciers are retreating very fast, but they leave you these nice polished outcrops. So you can see very well the structural network of faults and fractures. And here there is a modern PhD advisor for scale. Okay. That was my advisor, actually. We are in the Southern Alps. This is a batholith, or let's call it just a pluton made of granitoid rocks of some kind. The length here, there should be up here, okay, 10 kilometers, okay? And then we have been studying this fault for about 20 kilometers. However, the best outcrops are located about here, at the base of the glacier. This earthquake engine or fault is 30 million old, was at 9 to 11 kilometer depth, and is about 25 kilometer long. The point is that this is a sort of very simple experiment. I mean, this pluton here is this age, and it's like a big piece of granite that you put in this experimental machine where the two pistons are pushing from the north, basically, along these faults. So it's like an experiment where you put a huge piece of rock, granitoid rock, and there are two natural pistons, and you see what happens in your big sample. And the fault here is dextral. Now, this is the fault zone. It's very complicated. The glacier now is up here, and you can recognize the fault network. We can say that the fault zone is about half kilometer thick, and is made of more than 200 subparallel faults. And if you look better in detail, you can see these nice outcrops because the rocks are polished. We are at about 2,800 meter high here. And this is a block for scale. And of course, you can work on these faults and study the network. The nice thing is that there are also solidified friction melts. So we know that these faults were associated with earthquakes. And you can look here, and then you use a scanning electron microscope, and you see these things. So you have this class, the remnants from melting quartz and feldspar. Okay, many of you are not geologists, but basically this is the kind of seismic class you can see under the electron microscope. And I will tell you later why this is relevant. Okay, we can measure now things. In this case, the roughness, for instance. So now the scale is 100 meter here. So this is a fault that is about 1 kilometer long. So it can produce a magnitude 4 earthquake, for instance. And you can scan, we used it at that time a terrestrial laser scan. And then we made this sort of, now the scale is 20 meters. So you can study the topography, and there are fault segments. Now people will use photogrammetric techniques. At that time, we're using differential GPS, for instance, for many reasons. We can model this. So now the scale bar is 10 meters. This is the outcrop. And we can use a reference surface to study the waveness and so of these faults. Why? Because waveness is controlling a lot of the propagation of rupture and also of slip during earthquakes. So we can quantify, we make this a synthetic fault surface by doing several scans in several directions. Now there is a Manfro scale. So this is an example of this synthetic fault surface that come from measurements we did of faults that were seismic because they have this solidified melt decorating them. And there are depressions of only 15 centimeters here and culminations of 15 centimeters. They are the white in color here, okay? So just keep this in mind. Let's move now to another field case. We go now to the fault that...
Giulio, can I interrupt you 1 second? Why do you call that a synthetic fault surface?
Because it comes from the full, it's not a direct measurement of the fault surface. We start from the intersection of the fault surface here with the outcrop surface. So we have to make a Fourier analysis, Fourier transform analysis, and then we have to put together all this information coming from measurements done with different, well, let's say put here, with different, for instance, here for the same fault, which actually is also here and there. Okay, so then we have to make this synthetic structure. You understand?
Yeah.
So it comes from two-dimensional measurements to have a sort of three-dimensional pattern.
So it's all not known. So some is interpolated, basically. I mean,
excuse me.
I mean, it results from some interpolation.
Exactly. Okay. It's interesting. Then I don't discuss this, but then the waveness we get, it is basically self-affine. It's very similar to what people measured on fault surface exposed, just exposed in continuous, as maybe Michele show, I don't know, but because you can also make a scan of a fault surface, exposed fault surface. While here is not possible because the fault surfaces are welded by the melts, by the pseudotachylites here, by this, you see, they're welded. So I cannot see the fault surface. I just see the intercept of the fault, the intersection, a line, okay, between two planes. One is the two surfaces. One is the fault and the other one is the outcrop. However, we need that because I will discuss later. We were looking at how rough are these faults associated with earthquakes at depth, which is quite difficult to measure, to have ideas about. Another case, this is instead we move now to central Italy. So we are in the central Apennines. The mouse is moving very badly, excuse me. I'm getting you crazy. Okay, never mind. I quit. And now the fault is exhumed from 3 kilometer depth. The one before in crystalline basement was exhumed at about 10 kilometer depth. And my goodness, I don't know why the mouse is doing like that. Okay. Okay, I just don't move anything. And you can see in red the intercept of the fault surface with the outcrop surface with the bad lines in orange, okay? So this is the fault damage zone. Now we are in different rocks and Michele worked a lot on this. So you can appreciate the waveness of the fault. And now we can see here to the right should be what we call the footwall. So there has been a lot of work in the footwall mainly because the hanging wall is covered by the alluvial quaternary deposits. You can have an idea of the complexity of the main fault, which is relatively continuous, but also the presence of all these minor faults, and which is something that Michele have been studying and probably discussed it with you a couple of days ago, say 10 days ago and more. The fault is cropping out here, and yeah, and here the quaternary deposit, and you can recognize all these volumes with also the presence of these damage zones, which is a main question related to, you know, the energy dissipated during the main shocks and also maybe the aftershocks. How this off-fault damage forms. And here will be also the work of Nolwenn in these years to understand, because it's really curious. So these are what we call in situ shattered, for instance. I mean, you see all the fragmentation, but there is no shear, basically. The rock here is, let's say, exploded, I would say. Then you move to the faults, and you can find these mirror-like fault surfaces. Now there is a coin for scale. And also the question is, how do they form? We don't have a clear answer yet about when they form during the seismic cycle, and this is a matter of investigation. You can look also at the electron scanning microscope, and you can see, you know, structure of this kind. Now the scale is 5 microns. Okay, we're just looking about what we find in these natural faults. So this is what we see in nature. We see fault complexity and we see fault products. So let's move now to the lab. And this goes for the last half an hour. By call, build furnaces, observe and experiment without cheesing. Okay, let's follow Severino's, hint. It took a lot of time. And the first thing is, what is friction? If you ask the structural geologist, he will tell you friction, well, it's geometry, it's this stuff with bumps, with impeds. This is a fault surface, which basically makes it difficult, the slip of the block, which is missing here, because we see the fault surface with respect to the other block on the other side. So friction is somehow related to geometry. And actually, this makes a lot of sense. It also think in seismological ways. You have the concept of large-scale asperities in subduction zones. This kind of huge bumps can be former volcanoes, Guyot, and so on. But then if you ask to tribology, you go to the asperity at the micron scale. Okay, these are 10 to the minus 6 meters. And friction at the end is a rupture and chemical process. You are breaking bonds. If you want to slid this block to the top with the rest of the other one, you're breaking bonds. There is a rupture propagating, and friction is basically a fracture process. If you ask now to experimentalists, he will tell you, well, friction is 0.6, to make the story short. And this is what Byerly, which is probably, he made this very important contribution in the 60s and 70s, studying friction in rocks. Okay, what is friction? Now, the other point is, okay, let's say that this friction, which actually is a friction coefficient. I told you friction coefficient is the ratio of shear stress divided by normal stress and sample pressure and other things. Now, in rocks, in most cases, about 0.6. Then you can have some lower friction coefficient value, some clays especially. Friction coefficient can drop to 0.15, 0.1. And this is why also we have landslides. But let's go down again to the concept of power, okay? Because here, okay, we studied a lot the friction coefficient at low slip rates. But when you're in the seismic cycle, you can go from basically 0 when the fault, is in the interseismic period. But when you move toward the pre-seismic, an idea is that perhaps there is some precursory slip. And this slip on that fault patch may occur at 10 to the minus 12 or nanometers or less per second. But then this increases until you reach the seismic slip rates of the order of 1 meter per second and more. This part has been poorly investigated. There are technical difficulties. While the former, the one of low slip rates, has been investigated quite a lot. This goes again, as I told you, to the concept of power density, because if you slip faster, there will be more heat produced and dissipated per unit of time. And this increased temperature. So again, this goes back, as I told you at the beginning, temperature increase and of course also grain size reduction. So the role of temperature is quite crucial, according to me. So while from the low, when you have in this low power density range, what we call subseismic slip rates, and we don't, basically there is no radiated energy for these velocities, okay? We can measure with, of course, with seismometers. Well, at that point, this is described very well by what people call the rate and state friction law, that I will not discuss here, but probably some of you will use in his models. And also the friction coefficient is about 0.6, and the rate and state describes small variations of this value, which are very important for the nucleation of earthquakes. But when you go at 1 meter per second, because there is a lot of power dissipated per unit fall surface, well, we don't have any good, I would say at the moment, constitutive law, which is empirical in this case, but also we don't know even what the friction is. And actually, this is important when you want to run your models of earthquakes, because this is what Dunham suggested to use, is a sort of modify the rate and state friction law, where there start to be a very important dependence with the velocity. Now, this goes to these questions. So what are the physical and chemical processes active during an earthquake? And what are the physical laws that describe fault strength during earthquakes? So that's something we are still working on. And you must measure them, okay? Properties of rocks at high pressure must all be worked out by experiment. And this is especially true, I think, for high speed, because we did what we call high-speed friction, all these kind of experiments where we try to reproduce the slip rates achieved typically during seismic slip. Maybe machine learning will help here a lot too in the future. I don't know. Maybe we need more experimental data. And the problem is to produce this experimental data, because when you talk about earthquakes and seismic slip, you need to do experiment in these ranges, of slip rates, order of 1 meter per second. In some cases, the displacement can be enormous. You can think of the Tohoku 2011 magnitude 9.0 earthquake. Well, there is evidence of the relative motion between the blocks up to 50 meters, maybe 80 meters. Okay, these are the magnitude 9 earthquakes. Then the stresses are large, probably of the order of 50 megapascal and more, the effective stresses, normal to the fault. But then you want to put fluids inside, and there is powders sometimes that are produced. For sure, they will be produced at some point during seismic slip. So you have to confine this. And then if you want to get a constitutive law, well, you need to have nice data that are quite clean, what we call data reproducibility. Okay, so you have to make a good machine to do this, to confine your rocks and run the experiment. This is quite complicated, and we call these high velocity reflection experiments, to put all this together, and then in something that is not too expensive. So there are several machines. This is the one we built in Italy, and now it's installed at NGV. And you see the machine weighs 4 tons and is long 3.5 meters. And in this machine, you can install cylinders of rock that are about 50 millimeters in diameter. We are using this cylindrical shape, not because faults, they spin during earthquakes, but just because this allows us to have very large displacement in a small chamber, experimental chamber. And also the velocity can go up to 6 or more meters per second. So we can reproduce seismic slip rates, but also very low one. To do this, when you apply quite large normal stresses, here we can go up now with a new configuration up to 100 megapascal and more, using some particular pistons, electromagnetic pistons. Well, you have enough power. You need a lot of power from these sides to spin the rocks one against the other. In fact, basically, you have from here, we have what we call the rotary column, and these are the motors. And the power of this engine, this motor here, is about 300 kilowatts. So it's like having, is the power dissipated, let's say, from 100 Italian apartments. We have about 3 kilowatts for each apartment in Italy, okay? So you need power, you need torque, which can be even much larger than this using particular devices. And then you need normal stress. So we built this machine to do this. Now this is how it looks like today. We also can make experiments under vacuum. We are interested in these things. If you study friction, sometimes you don't want to have room humidity. Do you want to have humidity? Or maybe you want to do the experiment under very controlled conditions. So you pump in this chamber. So we have different kind of pumping systems, but you can pump argon. You can pump, do not have air in your system. Moreover, in the samples, there are particular kind of sorry, I have the bar just covering my screen. Okay, never mind. So we can also pump fluids in the experimental fault. Or so we have different pumps you can confine. We have mass spectrometers to measure the gas emission during the experiments. And now we are developing optical fibers to measure temperature, to measure strain, and so on. I don't think there is time to discuss all this. So this is one of the machines, but then the problem of this machine, which also has a lot of sensor to measure acoustic emissions and so on, is that we cannot play with temperature, which is something we want. Sorry, my screen is frozen. Okay. Can you hear me?
Yes, yes, we can.
Yes.
Okay.
Yes.
Okay. Okay, sorry guys. So that's the, I don't know what's going on with my connection. It should be the best one we have in Padova, but so this is the machine instead we have in Padova, where instead it's again a rotary machine, but here we play with fluids. The video is not going, I don't know why. Should go. But in any case, we install it. This is a rotary machine, now it's vertical. This has been bought and designed bought in Japan, designed by Professor Shimamoto. I worked with him for 2 decades now. And this is a very easy machine to use. And the advantage is that he designed a hydrothermal vessel. So the idea is to do experiments of fluid-rock interaction by pumping fluids where the temperature is up to 500 Celsius in rotary configuration. So the samples can rotate for large displacement, but also at speeds that about 1 meter per second, so seismic. But also we can work a lot at subseismic. I mean, this motor here can impose also extremely low velocities thanks to a gear system. So we can go down to 2 nanometer per second. So like, which is about 1 centimeter per year. So these are plate rates with a pressurized fluid up to 70 megapascal. So we can inject hot, and we can do experiments in the presence of hot water, very hot water, also in supercritical conditions. I don't know why this is not running, but anyway, this makes me upset, which is easy. Now there are all these rotary machines worldwide. Most of them have been installed in the last 10 years. There are 2 now recently installed in China, in Taiwan, then this couple I told you about in Italy, and then there is also in the United States, especially the one installed by Zev Reches in Oklahoma. What are the main results here of these experiments that are crucial for what I will discuss till the end, I think also for you? So the first one is that friction decreases from typical values, what is friction? 0.6, okay? For most rocks, there are some exceptions I told you that are clays I will not discuss here. However, when you're dealing with subseismic slip rates, so something less than, let's say, a few microns per second, friction is about 0.6. But then at seismic slip rates, something happens and friction drops down. This is the first experimental observation, and we have 1,000 experiments showing this. The second one is the strong dependence of friction with velocity. That's really crucial. This is an example of an experiment performed on calcite gouges. So basically the rocks you have the Central Apennines. And you can see how friction achieves a peak value, 0.8 in this case, 0.85, and then it drops down. When it's dropping down, when the velocity is increasing, this is the slip rate. In this case, we imposed the ramps up to 3 meters per second. The displacement I cannot see it but it should be of the order of meters because I have the bloody thing here covering. So the displacement was quite large, you see, about 4 meters amorphously. And then when the sample is decelerating, so you have in the deceleration curve, friction goes up again. So we have this sort of slip, we call this healing, this rapid increase in the friction coefficient at the deceleration stage. Then the other observation, which is quite crucial again, is that friction is basically, it's almost independent of the normal stress. So these are experiments performed with increasing normal stress, you see, but friction is in that range. Here is below 0.1, okay? So these are the three main conclusions, I would say, that are really crucial for a constitutive law or whatever. Strong velocity dependence and also little dependence when you start to play with, especially with high normal stresses, little or very low dependence with normal stress. Any proposed process should satisfy these observations: low friction, strong dependence of friction with velocity, and shear stress almost independent of normal stress, and then really crucial, must occur in nature. Okay, we are studying something that happens in nature at the end. Because of these, because of the rock types, because of the experimental conditions, environmental conditions, pumping fluid, hot fluids, whatever, well, there are 10, at least 10 of proposed processes operating at seismic slip rates. They're called flash heating and shock waves, frictional melting, superplastic behavior, silica gel lubrication, thermal fluid pressurization, and so on. You see, a lot. Guys, hypothesis non fingo. I mean, there is something, we must go to something simpler than that. These are the processes I put in orange, the one that may fit most of the experimental observation. And actually some of these, let's say, enjoy some field evidence, especially frictional melting is, we have found in the field this solidified frictional melts. So probably frictional melt occurs in nature in some cases. It's not the most common process probably. And then you can see also this mechanical fluid pressurization, thermochemical pressurization, superplastic behavior. I will talk about some of those. I'm just, because I have the last 15 minutes. And maybe I will show something about flash heating and frictional melting. So discuss the case for cohesive rocks and maybe non-cohesive rocks. Let's see. Solidified friction melts. So this is really the nice field evidence. And this is a movie. The movies are not going. I don't know why. I really don't know why they're not going. Let's see. Now they're going. Can you see this?
Yeah. Yeah.
I don't know if I do this. No, it doesn't want to. Okay, it's going now. Can you see this? I hope yes.
Yes.
So
yes.
these are experiments we did when we were testing the rotary machine. The rock is gabbro, so it's a very common rock. It's a very common rock in the oceanic crust. Gabbro is one of the most common rocks in the earth crust. And you can see the piston moving from left to right, while the one to the right was spinning at about 1,500 rounds per minute. So for this sample, the speed was about 5 meters per second. And there was quite an abrupt acceleration, you see, of from 0 to 5 meters per second in tenths of a second. The rock melts immediately. We can appreciate this using a high-speed camera, more in detail. So there is one frame every millisecond, and you can see white color, is more than 500 degrees Celsius. So you can see the extrusion of hot rock and probably melt. At some point, there are drops of melt coming out. Now we can put together these observations with the mechanical data. So this is shear stress, and these are the first hundreds of milliseconds of this experiment. So you can see the white spots in the left, and the friction is quite high until there is a drop once you have a continuous layer of melt, a drop in shear resistance. during the experiment. So we have two weakening phases. This is what we call flash weakening. So the initial weakening, but then there is the formation of these continuous patches of melt that impede a nice lubrication. It's a sort of mixed lubrication of the experimental fault, and then until there is a continuous layer of melt, which goes to melt lubrication. So we studied this thing quite a lot. But this is what you see if you stop the experiment at the beginning. So if you stop the experiment after 1 millimeter of slip or few millimeters, like in this experiment, you can find at this scale, this is 1 micron bar, you can see these patches of solidified glass. They are evenly distributed. There are some here, other there. They're not continuous. And this goes to this mechanism, flash heating and weakening. This happens probably in every earthquake, magnitude 0 earthquake, very small. You need a very small slip distance to have this. And this is, for instance, the dependence of friction with increasing slip rate. And there is a sort of critical weakening distance. When this is achieved, usually it's of the order in most rocks of 10 centimeters per second, friction drops down, start to go down. And this is a micro scale process, occurs at the Asperity scale, and it owns is a sort of nice constitutive law, okay? You have a critical weakening velocity, and also the friction evolves at some point with the velocity, okay? Then we move toward the steady state, or what we call the steady state, but once this critical beginning has been over, this critical weakening, initial weakening has been overcome somehow. There's a sort of threshold. The friction is still quite low. As you have seen in the movie, it's about 0.3. You start from a rock where the friction is at 0.7, okay? There is this thing happening, and then there are this evolution. We can discuss this, what we call steady state. Of course, there is melt, a lot of melt, a continuous layer of melt that is a glass once solidified, okay? And this is the kind of constitutive law that describes it. There is a nonlinear dependence of shear stress with normal stress. As you see, it goes with a power of 0 point something. Usually for gabbros, probably it's about 0.25. If you change the rock type, it may change slightly. But this is what you would expect, the gray line for a typical friction coefficient of 0.6. And this is what you measure. And then you can fit with this equation for in experiments when there is a continuous layer of melt. This constitutive law is quite complicated. It depends on a parameter W, which includes the viscosity of the melt. It depends on velocity V. It depends on some geometrical factors that I will not discuss here. What is nice is that you can compare experiment and nature. You find similar textures. So this is quite cool for us because, okay, what we are doing in the lab is something that happens in nature. There are some differences that I will not discuss, but these are details. The main message is we can produce these things and have an idea for frictional melting. So like Carolina Kostner, she's basically, sliding on the ice because of a bit of her weight, but mainly because of frictional heating happening here between the blade and ice. She produces a film of water that lubricates the blade, and she can, skate as she's really beautiful in doing that, in doing this. Something similar may happen in some earthquakes because of melt lubrication. Now let's go to the carbonates and why we have these mirror-like fault surfaces. There are many processes that can produce them. One is related to seismic slip. I will show this. These are experiments we have done in a rock, which is the Carrara marble. So it's a rock made 99.9% of calcite. It's a marble, so it's a different from a limestone, but who cares here? The point is that it's made of calcite. And you see this nice white rock, excuse me. The movie is not as good as the previous one using another camera. It's not even going. Yes, it's going. So there is a very rapid drop on friction. These are milliseconds. The target slip rate was quite high, 6 meters per second. The stress, 20 megapascal. You can see that after a few hundreds of milliseconds, don't worry, it goes. Few hundreds of milliseconds, friction is about 0. So there is a full lubrication. However, there is no movement of the piston here. Basically, there is no expulsion of material, very little, but then the temperature increases. This is not natural anymore because the displacement is enormous, 60 meters probably, and you can start to see this sort of lights coming out from the sample. The temperature here probably is 2,500 Celsius. These are called lime lights. These are very high energetic photons that are produced in these extreme conditions, okay? Look at them. In this case, we have calcite and we have decarbonation. What's going on here with these lime lights are related to the temperature where about 2,400 Celsius, where lime, CaO, is near melting, then a melting point. Okay. I will not discuss much this, but I will focus what happens at the beginning. So this is friction, this is slip, and these are two experiments where the target slip rate was slightly different. So this is the acceleration to about 3 meters per second, 6 meters per second, excuse me, and this experiment was kept constant at 3 meters per second. However, you can see that the friction coefficient in the two experiments is quite similar, and actually the friction coefficient is almost 0. Basically, we're measuring the friction of the machine here. In these experiments, we did more. This is Harvard, so there is a misspelling. We did a lot of experiments here. What was clear was the very important dependence of the friction coefficient with slip rate, for instance. Here you have the velocity function, abrupt acceleration, a slow deceleration, and you see the response in friction. However, friction can be extremely low, of the order of 1 megapascal in this case, after a few centimeters of slip. Hahn did this relevant paper in Science, sharing the same marbles many years ago, and he was also measuring the CO2 emission. This is something we did to show that you have this kind of reaction going on. He was measuring the temperature. Now we have better data for all these things. But the point is that we have chemical reactions. Breakdown of calcite to produce lime and CO2. This happens at more than 600 Celsius. And then if you shear more, at some point you will melt the lime. And this is where we observe that flashes, very bright flashes. If you stop the experiment after alpha meter of slip or less, you will find this on the slip surface, you know, this kind of texture. This is a field emission secondary electron image. The scale is 1 micron, and you can see this sort of pavement. The original grain size was 500 microns. And however, these things are 500 times smaller. Okay, they're only 1 micron. So this is something interesting going on. And this grain size reduction is something you can observe, especially below the slip zone. Again, this is the scale bar is 1 micron. We did several studies here. We want to understand what is the processes associated with this such a low resistance. And probably it's a mixed process between grain boundary sliding and diffusion creep. These are microphysical deformation, micro deformation mechanisms. This, I don't want to spend too much time on this, just to tell you how complex is nature, depending on rock type. And what is nice is that there are some constitutive laws that come from other kind of experiments where you can put together, you know, what is the expected flow stress or shear strength of this material at a given strain rate. So velocity of sliding for a given thickness of tens of microns or 50 microns. Then you need grain size, stuff like that, but especially temperature. Well, if you put these values, you can really fit this very, very low shear stress. If the temperature is high enough, which is something we measure, if the grain size, you will measure it at the end of the experiment. Well, and there is an activation energy. These are crystal plastic processes, so you need some activation energy and so on. However, you can really fit the experimental observations. So there are both textural evidence, but also this estimate that fit somehow. So depending on the rock type, you can have frictional melts, or you can have this kind of processes going on, maybe. And then we discussed about frictional flash heating and weakening before. So these are the very last minutes. So there are grind size dependent processes activating during earthquakes. Maybe yes. We are comparing now the natural calcite with experimental calcite after shearing. Could be. There are many reasons to have this fabric. I will not discuss this here. There are some similarities. What is interesting, perhaps, is that you can do, as I told you before, you can do a lot of experiments. Now people designing new gouge holders where you can pump the fluid inside. You can measure with high precision accuracy the temperature just next to the gouge layer. You can really, and at that point you study what people call the role of pressurization of fluids in weakening. These are, it takes a bit to describe this slide, but basically I want to tell you that now we are at the level where we can really dig a lot in these experimental observations and also in their reproducibility, and also measuring different variables at the same time that 5 years ago was not possible. For instance, pore pressure. This is a case where the orange is the slip velocity, the black curve is the fault strength. Here, the slip velocity was about 1 meter per second. And in this case was the gouges from made of calcite. So like what you can find in the L'Aquila earthquake slip zone. So in the earthquakes in the Central Apennines, if they are saturated in fluids. So this is the pore pressure and in the gouge, and we can measure these abrupt variations while there is an evolution in fault strength. This goes toward a better understanding in terms of what is the constitutive law for, I would call it fluid compaction and pressurization. Fluid pressurization. Probably I can skip this because it's a bit late. And so this goes to the experiments we're doing here in Padua about what happens when you have hot fluids and pressurize in this slip zone. I will not discuss this much. In case if you are interested in, let me know. Because what is coming out very interesting is that the physical state of fluid control the friction coefficient. So if it's liquid, vapor, or supercritical, it makes a big difference according to these recent experimental observations. Okay, yeah, I can drop that. And why this happens, there is no time. But I want to summarize these some constitutive laws. They're very complicated to use in numerical models. So this could be for flash heating and weakening. There is some dependence of I mean, this is for the critical velocity, but then you can get, from this, you get also the frictional values, how the friction how evolves with the velocity. Then you can have this complicated one, which relates shear stress with slip rate, and there is a normal stress in between. Or another one, which is a superplastic behavior, the one we discussed about calcite gouges. So it looks like, temperature matters. And you should go, perhaps, if you want a physically based friction law, that should include an Arrhenius like the temperature dependence. And so this is quite complicated to put in numerical models of ruptures. Sorry, sometimes this stacks. I'm sorry. So there can be other options. And then we go back to what I don't like much, but is best fit. So this is shear stress, this is slip rate, and you can fit this data set with this sort of constitutive law where this is shear stress for a given velocity, okay? There is a threshold that you have to overcome. So depending on which velocity, if you're below or above this velocity of about 1 millimeter per second, this constitutive, empirically based law works. However, this is based on experiments. So, but then you can also give forward, and you can just make a best fit of the slip weakening decay. So now it's friction versus slip. These are many different rock types. And you can make a sort of slip weakening law. So we have frictional coefficient, which depends on the dynamic friction here or residual friction during sliding at the speeds of about 1 meter per second, and then this exponential decay, okay? So you need basically initial friction can be 0.8 and basically a friction down here, and then there is some weakening distance that describes the decay. So you can apply this, and this goes to the numerical part, where we try to put fold geometry and fold friction together. I almost finished. This is an example for some work we did many years ago now, and we're using a code that related to that was developed for the Tohoku earthquake, where you have this is the Japanese coast, of course, and this is the fault that ruptured in a very simple model that ruptured during the 2011 magnitude 9.0 earthquake. Okay, and so let's hope it doesn't go. Sometimes stuck. So the next slide will be a sort of cross section where with Shane Murphy, we developed he made the code. I mean, he worked with this code with other guys from Naples and Dorito and other people. But the point is that this spectral element model, we tried to put the crustal, the properties of the crustal rocks, but also the frictional properties. So here you are at the trench. So we have some, we started several, we have some frictional laws basically that describe the slip weakening for this material. Materials up here, and then going down, this could be gabbros, could be serpentinites, and so on, going deeper. And so this we attributed basically to the mesh different frictional and geological, basically, and physical properties of the rocks. So this is an example of the model, if you ever run, yes. So the rupture propagating, you know, these are 2D models, and these are sort of simulated ground motions. Of course, now people can do much better, and they do it, like this one, okay? This is from Alice Gabriel group, where you can see the rupture propagating a three-dimensional. First of all, geometry really, clearly you can appreciate the role of geometry, and of course the propagation of the rupture. And of course there is some silicon weakening law to describe what's going on here, and that people in this audience can discuss much better than I can do. And I conclude, okay, saying this is basically the main message. Probably we know very little about earthquake physics. And here the idea was to use a geological, experimental, microstructural, theoretical approach to give a complementary view of earthquake physics. And as a geologist, so I can say a lot of bad things, okay? Of course, the first observation comes from the field one, you know, as Aurora also was showing, and working with Menandri and with these machine learning techniques, that of course the ruptured knucklite propagate and arrest in spatially complex faults. And this is something that also Nairé will show, the people that talk today, okay, by working, she will work on this, okay, to understand the role of stepovers and so on. So rupture complexity is controlled by the complexity, geometrical complexity of faults. Then the other observation based on experiments that we have that these faults then are duplicated during earthquakes in most cases. And this is independently of rock type. However, when you focus on the on-fault friction, let's call it friction because it's whatever it is, but it's the ratio, let's call it, of shear stress with normal stress. Well, they are the kind of frictional process depends on rock type and also ambient conditions. If you have fluids, there will be a different story. If there are supercritical fluids, can be a different story. If there are, you know, and so on. Most of these frictional processes are not well understood. I think the only one that is well understood is frictional melting. I can say, according, but not only to myself, I think to many people. The other one, they have some very good theoretical background, but no good experimental evidence or stuff like that. This is the case, perhaps, a bit of thermal pressurization. We have evidence, but it's damn difficult to do experiments to study it. Experiments, well, of course, they yield empirical and physical-based constitutive friction law that really, we need this, and this goes to several PhDs here, including the one of Elizabeth in Utrecht, to figure out what are the best laws to apply in these rupture models. Because now the rupture models can include quite a bit of these things, because they are so sophisticated, so rich, that really maybe we can do a good job in helping them, helping the modelers. Okay, so I think this approach here is one of the pillars of TREAD. This is why there are several PhDs dedicated. Some of you will spend quite a bit of time on this. So thank you for your time. And I think I ended with this in an hour and 8 minutes, something like that. Okay, so excuse me. I was a bit fast in some points.
Thanks a lot, Giulio. Excellent talk. Thanks a lot. It was very concise.
But there is a lot of stuff. I'm sorry.
Yeah. Okay. We have some time for questions. So if anybody has a question,
I bombed. I bombed.
Yeah, there was a lot of material. I have a quick one, maybe, Giulio. I was wondering during frictional, when you activate frictional melting, how does that affect the healing afterwards? I guess it does affect it a lot, doesn't it?
Yes, of course. It will default. So the what we call frictional healing is actually frictional welding in that case. So you can imagine that at that point the rate of aftershock will have a particular evolution in that environment. The point is that it's easy to find these solidified melts, typically in the continental crust, or even sometimes now in the oceanic crust when you look at them. Yes, maybe there are peculiar earthquakes where all the fault is decorated by these friction melts. They could be there are some earthquakes people studied in the Appalachians or in other places where you have also quite large stress drops, and they are typically occurring in a dry continental crust. However, the things are very complicated. Again, we have evidence now of production of pseudotachylites clearly in fluid-rich environments. But what we mean by fluid-rich is a bit of a story. There is evidence because the faults cut, veins that have chloride, some minerals that have a lot of water, and then these veins cut the pseudotachylite again. So they form cyclically in these environments. And also the pseudotachylites get altered very fast. So in that case, the welding is somehow, because of the fluid-rock interaction and alteration, maybe it's not so efficient. It's not so efficient because the glass becomes clay minerals, becomes chloride, so some weak minerals. So things are, your question is absolutely very, very important. There was a nice paper that came out recently, I think in Nature Communications, discussing the role of frictional melting and solidification in fault healing. It was an experimentally based paper.
Okay. By you remember?
I don't remember the guy. I read some of his papers, and I don't remember. I think he worked with Dan Faulkner.
Okay.
He's a young postdoc now. I think maybe I read this paper and made a very positive review. Maybe it was one review, I don't know, then maybe it was not published. But I really like the paper, the idea. I think it's published. And yes, the name is, my memory. I should check.
It's okay, don't worry.
I will.
Alessandro, you had a question.
Hi, yes. Just a question from point of view of a person who's trying to use this data or what is available for modeling of rate and state friction, for example. So what basically one of the main conclusion is how important is velocity, slip velocity in the frictional behavior, right? I was wondering, are still those experiments done with the subseismic velocity are still useful or not, or we should, or people should more.
My comment, there are many people here, I will be very direct. They are,
I want a direct comment.
I mean, they matter for nucleation, but then they don't make any sense to describe high-speed conditions because you don't have any more. Well, the concept of asperity is lost because they melt. You produce powders, and then the fluid expands because maybe there is trapped fluid there. You have this kind of thermal pressurization or whatever happens. I mean, this is something that Jim Rice discussed in 2006. He has a beautiful paper, where in JGR, where he discusses basically flash weakening and thermal pressurization in a very solid, okay, Jim Rice is, we are talking one of the, the masters. At that point, you cannot use a rate and state. I mean, you have to impose a velocity dependence, which is not anymore with the log of velocity, but is 1 over v. So friction drops with 1 over v, basically. This is what also Eric Dunham, I think he did in his rupture models at some point. So, but there is a lot of things to understand there. But for nucleation, the rate and state makes sense, although it's an empirical law, remember, it's an empirical law. And that's quite of a problem if we don't understand the microphysics, because it depends on your experimental conditions, okay? This is why several people in Utrecht did a huge effort to understand the microphysics of this, what happens in these nucleation stages. And so there must be an activation energy, there must be something going on in terms of the microphysics. I don't know if I answered to your question, but yeah, at the end, you must be also efficient in terms of, what is the most simple law that is, you say, computational, computational
efficient.
Simple, okay, and then I get a reasonable result. However, I would stress one point, the velocity dependence. That's something that David already make the point. Because if you make a simple slip weakening law, then this is not what we see in the experiment. There is also an increase when you drop down the velocity, okay? So you need to introduce in your model something that allows friction to increase again at the end of slip. This is instead, of course, is inside the rate and state friction law because it basically is a velocity dependence of friction. I don't know if I answered to your question, but
yes, definitely. Thanks.
Okay. Are there any questions by the students? That would be good.
Yeah, don't worry to ask.
Yeah, you can ask silly questions. I mean, there are no silly questions actually.
Exactly, there are silly answers. That's for sure.
Can I have a silly one for me, maybe? I was wondering about the roundness of the chase of the microstructure in the friction comparison that you make between the natural picture and the laboratory made picture. As I remember, the natural one was more angular shape and the laboratory one was rounded. I just wondering why maybe you explain that, or what's the reason for the round?
I didn't explain much, probably. Yeah. What else? No. I mean now there are many details there. I think you are discussing. You were discussing about the frictional melts. Can you
exactly?
Yeah,
exactly.
Yeah, you see, there are 100 slides. Don't do it. Okay, I'm a beast. Okay, so that's
exactly.
that comparison.
Exactly.
Yeah. Well, actually, the shape is not probably so different. There is a bit. I mean, some people did the grain size, the shape analysis. It depends mostly in the natural case. I think this was a small fault. the displacement of this fault I measured in the field was probably 10 centimeter or less. If you go in faults that have larger displacement, you will find the grains are more and more rounded. And this is because if the melt layer is bigger, or the melt layer is thicker, it will cool more slowly, and then there will be more melt rock interaction. So especially for feldspars, I don't know if you're a geologist. The point, basically this is a rock formed by quartz and plagioclase. So you find fragments of the host rock in this thin layer made of plagioclase and quartz. Now, in these frictional melting processes, what matters is at least in this case for this rock, is an individual melting point. That means quartz, for instance, melt at 1700 Celsius, okay, while feldspar melts at 1200 Celsius. So it melts, plagioclase melts more than quartz. However, so this is basically because it's rounded. But then if you allow quartz to stay in the melt for hours, for minutes and hours, so yeah, okay. These sharp boundaries, they will start to become rounded. So the shape is controlled by the interaction of melt, the time of interaction with melt and class. Sorry, I have a friend of mine bringing the wine here. Sorry. So your question, it makes a lot of sense. And actually there is a lot of discussion about the information we can get from these solidified frictional melts. Here they're a bit more rounded. This is an experiment. I think the slip was 10 meters when I did this in Japan many years, 20 years ago now. And there are also differences. You see the matrix on to the right in the experiment is a glass. This is a real glass. We did also microgamma spectroscopy recently on this. So we are sure this is a glass. Also, I mean, it's very homogeneous. In the natural one, instead, we have what we call devitrification process. So the glass devitrifies, and there is formation of biotite and other minerals here, and other strange minerals I will not discuss. But there is devitrification because we have 30 million years. There is a bit of fluid percolating in the fault, and this alter slightly. So there are some differences also. Yeah. Excuse me for the interruption.
No, thank you very much. It's perfect. Thank you.
They bring us the wine that we bought all together. Yeah, 20 people buying wine for.
Good.
I shouldn't say this in a seminar.
Well, I mean, it's a private seminar somewhat.
Diego.
So last question maybe, or anybody? Or otherwise, we can let Giulio enjoy his wine. I don't know if you're going to have a drink now or not, but
no, this is
for later. Okay.
No, I have a meeting in a few minutes. Yes,
All right,
a panel. Yeah.
All right. Let's see. You still have to be a serious man then. Okay.
Well, no.
Yeah.
It's bad. Yeah. Okay.
Thanks a lot, Giulio. Thanks a lot. That was an excellent talk. So we can stop here, and thanks everybody for attending it. And well, if you have any questions and you didn't, I don't know, you don't want to ask them directly, just send an email to Giulio, and it will be it has been recorded, so it will be you can watch it again if you want.
Yes, please drop me an email, and of course I will try to follow the next seminars. I'm very interested in the first half an hour. It was very nice to listen Aurora and Irene.
Yeah,
I really enjoyed that a lot.
Yeah. We'll keep doing this.
Yeah. So
Okay.
I'm sure Neire will have a lot of things to say in a couple of months from now already.
Yeah.
She just started, so of course.
Yeah.
So I really enjoyed that. Thank you for organizing this, David, and for the people here.
Okay. So bye everybody, and enjoy your week.
Ciao.
Bye.
Ciao, everybody.
Bye.
Thank you.
Bye-bye.
Bye.
Thanks,
Ciao.
Julian.
Bye.
Thank you.
Bye.
Bye.
Goodbye.